Even though it's not acting on the scale, it's still there.
Okay.
An actual application of physics. Whoa, who would have thought? All right. Questions before we do the next exciting installment? Because we're about to put box on ramp. All right, box on ramp. Slowly heading towards the test level problem. Now I put the symbol theta here to indicate that there's an angle. I think you can just clearly see I've drawn an angle there. In 151, actually 131, 151, 251, that angle will become important because you'd be asked to find the acceleration of the box. But just doing the force diagram, being able to add the forces geometrically, head to tail, is something that's 110 level, but using that angle is not something that we're really going to do anything with other than just recognizing some of the forces will be not vertical or horizontal. The ramp is part of the ground, so that's one of the reasons why I have nothing there. If I separated the ramp from the ground, then, well, we've just introduced another object. I don't want to do that yet. My recommendation is that when you are drawing the box, draw it in the same orientation as it is right there at an angle. Some students will straighten it out so that the sides are parallel, or vertical and horizontal. That has caused problems coming up. So I would not recommend that. All right. Is there anything we can get rid of?
Other
Okay.
tension.
Yep. Let's do friction last, since that's the one that we have. Is the new one. I think weight's still the easiest. Which way is the weight acting on the box? This is how down is defined. The direction of the weight on the smaller object is always down. And then which way on the ground? Now, I have the box here. There's weight acting up. It doesn't really matter where I draw my up arrow for weight, just so long as it's touching the ground here. Draw it here just because my box is there, or I could draw it here just because that's where the box really is. But somewhere on this thing I'm calling the ground, there should be weight. And that's it. I just have the one small object, so weight done. Normal force. But up from the box. On the box?
On the box.
Up. That's, make sure I heard you correctly.
Yeah, up.
What is the direction of the normal force with respect to the objects?
Up to the box.
On the box.
Is the box not sliding?
It actually doesn't matter which way if the box is sliding or not.
Oh, okay.
It matters which way the box wants to slide, but not if the box is actually sliding.
Okay.
So, what is the direction of the normal force?
Up onto the bar. I don't know.
Isabella, what'd you say?
Perpendicular to the surface.
Yes, perpendicular. Remember, normal means perpendicular. Or look at the chart that we did right before this. My surfaces of contact are like this. So my normal force is perpendicular to that. Rookie mistake, whatever number. Some people always want normal force to be up or down. Normal force could be in many different directions. Right now, there's a normal force pushing on my feet upwards. There's a normal force pushing on my hand towards the back of the room. And I have only two objects, so only one place of contact, and so normal force done. All right, friction. Which way does the box want to slide with respect to the ground? Friction hates that. Absolutely despises it. It's going to do whatever it can to stop it. So since the box wants to slide down the ramp, the friction is acting up on the box, up the ramp on the box. So friction is acting, that way. Friction opposes desired relative motion. So whether the box is actually sliding or not, friction is still acting that way. But forces come in pairs. What's the other part of that pair? As we'll get into in chapter 4, if the box is not actually sliding, it's called static friction. If it is actually sliding, it's called kinetic friction. Some slightly different rules for those two, but we can hold off on that. Either way, there's friction acting up the ramp, whether it slides or not. Any questions right now? All right. Because this is ultimately sort of a marathon session, why don't we take a break? Especially since Kimberly walked out. It's time. It's time. Mistake 5. Mistake 5. By the way, what we did on Monday, the part that I recorded is posted. If you go under coursework, chapter 2, but if you haven't done the course entry, even one attempt at the course entry assignment, you won't find it yet, but once you can see it, coursework, chapter 2, and then down at the bottom, something clever like physics 110 class lecture, something like that, and then there'll be a YouTube link. So again, the stuff that we're doing today, you'll see eventually. All right, so on a problem like this, I've now introduced the rope, so obviously tension's going to come into it. There comes a question for some students about, do you talk about the forces acting on the pulley with the ground? And so part of what I've done here is, since I've drawn the pulley attached to the ground, I'm not worried about those two as different objects. The pulley and the ground are all part of the same thing. So when we get to the test level problem, I will separate the diagram for you just so that you know what is considered a separate object and what is not. So pulley is part of the ground. Go to the checklist, can get rid of anything. Oh, let me throw in one other thing. Ideal pulley, ideal rope. Ms. Sasson, the other full-time physics instructor, calls it the magic rope and a magic pulley. So, ideal pulley and ideal rope, massless and frictionless. And pertaining more to the rope than the pulley, stretchless. Microsoft Word refuses to admit that that's a real word, but we'll get it in there somehow. Unless one of you brings Microsoft down before the end of the semester. Or I guess before the end of the 8 weeks. Stretchless means that the length of the rope stays the same. So I'm not going to have one object moving and the other one still staying behind. They move at the same time. All right, can we get rid of any of these forces not involved in the problem? That is correct. And that's it. Only one we can eliminate this time. All right, so let's start with the simple one. Weight. Is weight involved? Well, I guess weight is involved because no one threw it out. Weight is acting on what object and in what direction?
Is acting on weight 2. Yeah, on number 2.
Acting which way?
Upward, downwards,
It's one of those two.
upwards. Acting upwards.
So if I cut that rope, mass 2 is going to go flying upwards
It's gonna go down.
because weight's pulling it down. And where's the other part of that pair?
On ground.
Okay. They're pulling each other toward. They're pulling towards each other.
On number 1, 2, right? For number 1, 2, right, it's going down.
And up on the ground. Now I drew it at that point. If I could have drawn it down here just as easily, just so long as it's identified with the ground. All right, so that's it. I just have the two objects. The rope here, if we got into far more sophisticated analysis, the rope has mass, but I made this an ideal rope, so it has massless. So it is massless, and massless objects do not have weight. So therefore, there's no weight acting on the rope. Some students will still put a weight on the rope, and I don't mark it wrong, and that's just more detail than we need. So weight, we are done. That's meant to be a check mark. Let's try that one again. There we go. Normal?
Up on one.
I heard up on one. And the other part?
Down on one. And up on 2.
What's pushing up on 2?
The ground, the bottom part of the ground. Oh wait,
They're not touching.
sorry.
No normal force on 2. That is a common mistake there. There is another normal force pair though.
The pulley isn't the rope.
And
Is it the rope on the wheel?
yeah, pulley and rope. Not pulling ground because they're part of the same object. That would be called what's called an internal force. But there is a normal force between rope and pulley. It's anywhere there's contact. So we have, I don't know the exact direction. I didn't give you enough detail to know exactly which way the normal force is acting on the rope. So it's somewhere in this range from between directly up and directly to the right. So I just generically draw something in that direction, and I'll call it Y sub R for rope. And the other one should be in the opposite direction, acting on our pulley ground combination. Anything else touching?
The rope to the box?
That's where tension's gonna come in.
Okay.
And I have a video talking about tension in the relationship with normal force or friction or tension, and I think the label of the video, does tension exist? Oh, over here. All right, friction.
Box one.
Acting which way on box one?
That way, right?
So left.
Oh, wait, I don't.
Right, you said to the left, you said,
Cause I'm thinking like, well, you already said you're not telling us which way, like, which one's pulling up or down, whatever. But I was thinking like, one will be going like, one will be going this way
okay.
because.
No.
I just
You
think
wanna
that
roll
one
there?
will be going that way because like, it's pulling against like, the, I don't know, either the pulley or two. I don't know the proper terminology.
All right, so what help that out?
Friction go that way because two's going one this way.
Okay, so which way does one want to go?
To the right, to the left.
No.
To the
So
right.
it's being pulled.
If I set up this situation, you're saying that one wants to go that way?
Yes.
The friction.
Okay, that's a different question.
Oh.
If I set this up and I let go, which way would one go if it's
Right.
frictionless?
Right.
Yeah, friction, so without friction, one's going that way and two is falling. So one wants to go that way, so friction is acting to oppose that. And then on the ground.
Yes. Thank you.
Now, one requirement for friction is that there's normal force pair. Normal force is a necessary condition. So I have two normal force pairs. I have the one between one and the ground and one between pulley and rope. So those are the only two places friction could possibly exist. We got that pair, got that friction. But friction here, well, these are ideal, so they're frictionless. So there's no friction acting between pulley and rope, just because of the way we set it up. We don't add, and even then, I don't think we do in 110. In the more advanced classes, it would not be until we got to rotational motion that we would remove that ideal. Basically in physics, you set up with a nice ideal, you get rid of all the stuff that you don't care, that is just too complicated, and then over time, you just keep adding more and more reality. And then at some point, you just detach yourself completely from everyday life. And you'll get particles that no one has ever seen. All right, so friction's done. Tension, all right. Tension is a pulling force. Think about it this way, if the rope broke, what would happen? So if I clip the rope here, what would happen to two? So which way was the rope, what was the rope doing to two? Absolutely. So I have a tension here, FT. Now they come in pairs. Where's the other part of that pair?
One.
I saw the air point down on straight, okay. That is the tension pair right there. But now, there was a question earlier about there's contact there, so is that a normal force? And so this is part of what that video goes into. I don't know how the rope is attached to two. Is it an eye hook and I got a rope sort of tied there? In which case, there is a normal force. Or is the rope embedded in mass two? In which case, that's a friction force, or potentially some other thing. So we don't know how they're touching each other, so we'll just, whatever it is, we're gonna call it tension. All right, there's another tension pair.
Between one and the rope,
Which way is it acting on one?
to the right.
I hope so. Because realistically, if I set this up, one is gonna be moving to the right, there's gotta be something doing it. So I have a tension here, and then tension there. This is a tension pair here, because I said forces come in pairs. That's one of the pairs, and that's another pair. Because it's an ideal rope, that magnitude of force and this magnitude of force are the same. If it's not an ideal rope, they're not the same. So if you want to put subscripts in, and this is optional for the ideal rope, these have to have the same subscript, and these would have the same subscript. But you don't, for the same rope, you don't need to put subscripts in. But it's not wrong if you do that. And, oh, that's the last one, tension. There should be a pair of tensions at the end of a rope. Questions before I now throw this onto an angle and then hit the test level problem? Make that part of the ground. Draw my object separately. The ramp is part of the ground. Now I'm going to make the pulley part of the ground also. So I've got one, I got two, and then I've got rope. I will say, let's do friction last.
Is it best to always do friction last, or is that just like the problems that we're doing now? Best to do it last.
Well, we did tension last that time. My personal recommendation is do the easy ones first. So to me, that's weight and normal force.